Okay, so our last topic before we get to Runga is going to be over converting a nth order equation to a system of equations, and then being able to use either Euler's method or Taylor method or even Runga method to be able to approximate a solution to the differential equation. So let's look at it. Here's our last topic in section 5.9. We can also approximate nth order differential equations of the form we have the nth derivative of x equal to some function of in terms of a function in terms of t, which is my independent variable, and then the derivatives of x up to the n minus 1 derivative. So x prime, x double prime, all the way up to the n minus 1 derivative of x. Okay. Again, this function could have all of these terms or just some of them. So it might include the independent variable, it might not. It might include x prime or x double prime, it might not, and so forth, right? But it could if it wanted to. So we can also approximate the nth order differential equation of the form given by this by converting it to a system of equations and then approximating the solution. Okay. So, and you probably have seen this in differential equations when you guys took it, where you had a nth order differential equation, and we can convert that nth order differential equation to a system of equations. And that's what we're going to do here to be able to solve for this the solution to nth order equation. Again, we're going to just stick with a very straightforward differential equation, a second order differential equation. I'm going to convert that second order differential equation to a system. So let's look at an example. I want to approximate the second order differential equation. Again, it's an initial value problem. X double prime plus 3x prime plus 4x equal to 2, where we have x of 0 is equal to 0 and x prime of 0 is equal to 1. Remember that if it's a second order differential equation, it's an initial value problem, we need to have two, to be able to find a unique solution, we need to have initial conditions for both the function and its derivative, okay? And so we want to be able to approximate this solution. And the first thing we're going to do is we're going to convert this system, this equation, to a system. And how do we do that? Well, you might have learned it a little bit different, but it's about the same thing. I'm going to say, well, let u equal x and v equal x prime. Okay. Let u equal x, let v equal x prime. And what we're going to do is we say, okay, what is the derivative of u and what's the derivative of v? Thus, u prime and v prime. Well, what is u prime equal to? U prime is going to be equal to x prime, right? But what is x prime? Well, x prime is v. And we'll say let v prime equal x double prime. Well, what is x double prime? If I look at this equation that I have here, x double prime I can actually solve for Let's solve for x double prime. I'm going to say x double prime is equal to, in this case I could have minus 3x prime minus 4x plus 2. So x double prime, I could really write that as negative 3x prime minus 4x plus 2. But what in the world is x prime? Well, x prime we already said was v, and what's x is u. So finally I can write it as a system. In terms of u and v, u prime is equal to v, v prime is equal to negative 3 times v minus 4 times u plus 2. Okay. Now what are my initial conditions, right? Well, we know that x of 0 is equal to 0. So I can say, well, x is really u, so I can say u of 0 is equal to 0. And then I have x prime of 0 is equal to 1, but x prime is really v, so I can say v of 0 is equal to 1. Okay. And here's my system. I have u prime is equal to v, I have v prime is equal to negative 3 times v minus 4 times u plus 2. And guess what? Now we have a system of equations just like we did before in the previous that previous video where we can either use Euler's method or Taylor's method. Let's use Euler's method here. To approximate the solution. Now, when we do this, right, what we're really trying to solve for is going to be the value of u, right, because u is x. Right, so if we figure out what u is, we know we're actually looking for the solution for u. So when we solve for this Euler's method, so we have u sub n plus 1, which is what we're trying to solve for, because u is equal to x is equal to u sub n plus, in this case, it's going to be h times v sub n. And then v sub n plus 1, which is our first derivative of x, is going to be equal to v sub n plus h times the quantity, negative 3 v sub n minus 4 u sub n plus 2. Okay, where we have u sub 0 is equal to 0, v sub 0 is equal to 1. Okay. And like I said before, we can now pick a step size for h, right? Pick a value for our step size, and then use that to kind of approximate our solution. And whatever the value of u that we're looking for, right, that would be our approximation to the solution of this differential equation that we have here, right? V will give me the approximation to the derivative of my solution. So u will give me the approximation to the solution, v will give me the approximation to the derivative of the solution. Let's look at one more. Let's approximate the third order differential equation. And we use Euler's method as well. Notice that I don't want to deal with Taylor's method just because it gets big, right? We've already seen that it can get huge. Let's approximate the third order differential equation. So example, approximate the third order differential equation. Here I have x triple prime is equal to t plus x plus 2x prime plus 3x double prime. We have x of 1 is equal to 3, x prime of 1 is equal to negative 7. We have x double prime of 1 is equal to 4. So this is my initial value problem. Okay. Again, this is a third order differential equation. So when we had a second order differential equation, it broke it up into two first order linear equations, right? So when we have a third order system of equation, right, it's going to break, when I can do this conversion to a system, it's going to break it up into three equations that are first order. Okay, three equations that are first order. So let's do what we did before. Let U equal X, right? Say let V equal X prime, and then I'll say let W equal X double prime, right? So notice that I go up to one derivative lower than my the order of my differential equation. So this is a third order, so third derivative. So I'll go over to the second derivative here for my substitution. And so now let's plug in. So we have U prime, right, is equal to X prime, or V. V prime is equal to X double prime, or W, right? W prime is equal to X triple prime, which is going to be, in this case, we already see it is T plus X plus 2X prime plus 3X double prime. Okay, and now we have our system, right? We have our system of equations. What is it? Oh, yep, U prime is equal to V. V prime is equal to W. W prime is equal to T plus U plus 2V plus 3W. Okay. Where I have what U of 1 is equal to 3. V of 1 is equal to -7. And W of 1 is equal to 4. All right? And let's just write down Euler's method for this, and then we'll be done with this, and we can talk about Runge-Kutta next time. All right? I promise we'll talk about Runge-Kutta. You might wish I had not talked about Runge-Kutta by the time we're done with it, but them's the breaks. Okay. So let's put down the Euler's method version of this. Again, we're solving for, when it comes down to it, right, what we're really interested in when we want to be able to solve this differential equation, and we're really interested in the solution for U. V is actually going to give us the solution, or approximation to the solution to the first derivative. And then W will give us approximation of the solution to the second derivative of that equation. Okay. So this is what we have. Euler's method, we get U sub n plus 1 is equal to U sub n plus h. In this case, what it would be V sub n. V sub n plus 1 is equal to V sub n plus h times W sub n. Okay. And W sub n plus 1 is equal to W sub n plus h times the quantity of T sub n plus U sub n plus 2V sub n plus 3W sub n. Okay, where we have U sub 0 is equal to 3, V sub 0 is equal to -7, and W sub 0 is equal to 4. Okay. Right, and that's Euler's method for this particular example. All right. And again, we could, if we wanted to, we can approximate the solution doing this, but let's not do that on the board. It's not enough space. But it's a good exercise to kind of do this at home if you can, and just approximate the solution to this differential equation using this system that we have here. All right. Well, that is it. And next time we'll talk about Runge-Kutta. All right.